So today we are going to discuss about the topic of neural network basics, which is the lecture 2. So let's start with the neural network example, and we will first look at some of the theory parts or the notations that are commonly used in neural networks. Uh, Here I have used some of the notations a little bit mathematically inclined, but that is just for you to get the basic notations into your uh, lesson, right? Other than that, we are not going to going deeper into the mathematical notations that we have described here. Right? Suppose we have 1,000 images, right? Uh, where uh, the images can either be cats or not cats, right? So you have a set of images which are either having cats or not having cats. Your task is to classify whether a given image is either a cat or not a cat, right? Because the number of data points are 10,000, right? We can take m as 10,000. So generally we take the data set size as simple m as a convention. So here we take m as 10,000. Uh, in this case, because this is a binary classification problem, and because there are only two possible outcomes, we can take them as 1 and 0. And we can use this notation where uh, y can either be 1 or 0, right? So in this case, we can keep take 1 for cats and 0 for not cats, right? Or in the other way if you want, right? So there's no problem, right? So in this case, this is how we have defined our problem. When it comes to neural networks, same as in the machine learning problems, we have to map all the information into x values and y values, or independent variables and dependent variables. In When it comes to neural networks, you have to have numerical values for both uh, independent variables and dependent variables. So in this case also, we have to make sure that our x variables are uh, numerical values and y values are numerical. So already the y value is numerical, right? So because they are binary, it can have either 1 or 0. So let's see what are the x variables, right? So because this image, if you take any image, say that each image is size of 64 by 64, right? In that case, because there are three channels of the colors, right, in a RGB image, where red channel, green channel, and blue channel, there would be three channels for each pixel. So there are 64 by 64 number of pixels in a particular image. Because there are three channels, red, green, and blue, we have to multiply it by 3. So in that case, for each image, you can have 64 by 64 by 3, 12,288 number of pixels or pixel uh, numbers, right? In a particular image, right? So in that case, because each pixel has because there are 64 by 64 pixels, and for each pixel there are three channels for each image. So we have to multiply it by 3. Then there would be 12,288 number of features per image, right? So we can take this number of features per image x as nx, right? So in this case, we can define x belongs to a real number with number of features equal to 12,288. So this is how we give the notation for x variables, right? So here you can see the notation for y variables for binary classification. The number of data points are 10,000. So let's start our problem and try to solve it using machine learning. If we take m training samples, right? So we know in this case there are m is 10,000, right? So uh, for the notation purpose, just take m as just m, right? So then the data samples would be like this, right? Right. So each data sample can be represented by a couple of parentheses, and these parentheses sets are separated by commas, and all these samples are included in this braces. Right? In the first data set, there would be x1. So this is the first images, first image, x number of x set of features, and this is its y value. Right? And for the second image, this is the independent variables. This is the set of independent variables, and this is the dependent variable. For the mth image, this is the set of independent variables or x features, and this is the dependent variable or the y value, right? So there would be m number of data points for m number of images. Right? So this can also be represented in a different format like this as well, right? So you can use the capital X notation where X, so in this case, you can see it can be represented as a matrix, right? So this X and Y are matrices. So we can take the first data sample as simple X1 for the first data sample. There's a space and there's the X2 for the second data sample, and for the mth data sample, we can take as XM. Right? So you can represent X in this format as well. Right? So because there are nx dimensions per x and there are m number of samples, this is the dimension of x, right? For the y, similarly, we can have m number of data points for each m number of data points. This is the first image's y value. This is the second image's y value, and so on. This is the mth y value. Right? And the dimensions of y would be like 1 times m, because for each y value, there's only a single value. Uh, it can either be 0 or 1, right? And there would be m number of data points. So this is the dimension of y value, right? This is the dimension of x value. So these are the notations that we are going to use in machine learning in these kinds of problems. So I have used these notations not because we are going to use these notations further down our lessons, but just for your knowledge, so that you can use this knowledge when you are uh, having some issues with the, so when you find some reference materials with this kind of content, or you read some papers, research papers or publications or machine learning books which have the representations like this, so that you can understand uh, what it means by these notations with related to neural networks and their data sets and so on. Okay, so the math part is over. That means the notation related math part is over. So sometimes if you are not that much familiar with real analysis, or you are not from the math background, you may find some issues. What are those so what is the difference between this R value and why do we use it? So it says it's a real numbers, right? So you don't think too much about this one, right? So if you are interested, you can find further, right? So we here says that this is the format, this is the dimension of y, right? This is the dimension of x. So in here we are using capital letters for x and y because those are matrices, right? So in this case, this x1 is a can be a vector in the vertical direction, right? X2 can also be a vector, xm can be a vector, right? So, but y1 is a scalar, right? So because this the dimension of is 1, because it is either 0 or 1, it can be a binary value. Y2 is also a binary value. Ym is a binary value, right? So x is a uh, so in here you can say that x is a matrix and y is a vector, actually vector transpose, right? So its direction is like this, but there's no depth in this vector, uh, right? So y1, y2, ym are just a set of sequence of values, right? So if you are not very clear at the first glance, right, don't worry, just go through the content, take your time, and start to read it slowly and try to take it into your mind until you remember and until you map all these notations if you are not that much familiar with these notations, right? Don't worry, we are not going to use it in these lessons or most of the upcoming lessons, but this is necessary for you to have the basic understanding about this these mathematics, right? That is why I have introduced these notations. So now let's move into the logistic regression. We have discussed about logistic regression, but here we are going to discuss it again to rem remind you what we have learned about logistic regression, right? So logistic regression, you know, it is a can be used as a binary classification, binary classifier, right? So in this case, we can use the cat images and apply our binary classifier with logistic regression to classify the cat images, whether it is a cat or not, right? In that case, how we are going to predict the value is using the y hat, right? So this we use the y hat to denote the predicted y value, right? So when the machine learning model predicts something as the dependent variable, we generally give the notation as hat, right? So when the dependent variables predicted value is generally denoted by y hat, right? So the y hat is given by the sigma, which is the logistic function of w transpose x plus b. You know what is w transpose, right? W is the weight vector, weight matrix, and multiplied by this is the input, right? X input plus bias, right? So this one is a linear equation, linear statement, and once you apply this nonlinear function to this linear set of operate equations, linear statements, you will get a nonlinear uh, outcome, and that is known as the logistic regression, right? So the sigma can be denoted by this logistic function. If you can't remember, this is the logistic function, right? So this is a well-known function. Yeah, E is the Euler's constant, right? Uh, to the power minus Z, right? So sigma Z is 1 over 1 plus e to the power minus Z. It would have a distribution like this, right? So this is the logistic function where when it is 0, when the value of Z is 0, the value sigma Z would be 0 0.1, 0 0.5, sorry. When the sigma is greater than 0, it is getting increased and it is moving towards 1, right? So at the infinite, the sigma Z goes to 1, right? When the sigma goes to the negative side, it is reducing from zero point 0.5 and it is moving towards 0, and sigma Z goes to 0 in the negative infinite, right? When the Z goes to negative infinite, sigma Z goes to 0, right? This is the this is the graph of this function, right? Okay, for the ith training example, right? So we have denoted this one this logistic function for in the general case, right? So, but when you are training for the ith training example, when you're applying the ith training example, so you can use the notation uh, parenthesis I, right? So in this case, the I has moved a little bit up, but assume that the I is inside this parenthesis, right? So in all the cases, right? So it's a mistake, right? So I should be in the parenthesis in this case. Y hat I, that means for the I training data set, for I training example, predicted value of Y should be equal to sigma of WT xi, that means ith examples x value plus B, right? WT and B are parameters, right? Sigma is this uh, uh, logistic function, right? So the logistic function, so once you, the logistic function would be like sigma I, that means ith data point sigma value. When you are applying it to the this logistic function, you would get 1 over 1 plus e to the power minus z I, right? Z I is the value that you get inside this sigma statement. And once you apply it to this statement, you get the final output. That means y hat I, right? Okay, so now let's move into the loss function of this logistic regression. Right? I think you can already remember, right? So this, if you are, so when it comes to linear regression, you can use mean square error. If you have used mean square error for logistic regression, it would be like half of y hat minus y square. But the problem is that we can't use mean square error for as the loss function for logistic regression because it is not having a single minimum point, right? So it cannot be used in this case for the logistic regression. So the best function generally used for best loss function used for logistic function is binary cross entropy loss, right? So the binary cross entropy loss is denoted by this one, right? So L, so loss of y hat is the predicted value, y is the real value or the ground truth value. So when you give the real predicted value and the ground truth value, you can find the difference. So from this difference, you can get the loss, right? So this loss is defined by this function where it is also because it's entropy is generally given by negative, so value, so it starts with negative y log y hat plus 1 minus 1, so 1 minus y log 1 minus y hat. So this is the cross by the cross entropy loss. When y is equal to 1, loss of this function would be, so when y is 1, this one would be y 1, so it would be log y hat. Uh, so when y is 1, so 1 minus 1 would be 0, so this part would become 0, so it would be minus log y hat, right? So this would be minus log y hat. So if you take y equals to 1, when you try to reduce L, because in uh, for this optimization in the during the training process, what we are trying to do is we are trying to reduce the loss, right? So you are going to reduce the loss value. So when you're reducing the loss value, you have to reduce this value. Reducing this value means you are trying to increase, because this is a negative value, you are going to increase the log y hat. That means if you are going to reduce this value means you are going to increase the log y hat. Increase the log y hat means increasing y hat, right? So that means if y equals 1, what you are trying to do is increase the y hat. If y equals 0, right? Y equals 0, this y will be 0, so this term will become 0, right? This y will be 0, so then this 1 times log 1 minus y hat, this minus would be there, right? So in this case, minus log 1 minus 1, sorry, 1 minus y hat, right? So this would be the term when the y is 0, right? So during the training, when you are trying to reduce the loss, then this value should become high, right? So we are trying to increase the log 1 minus y hat. So that means we are going to increase 1 minus y hat. That means we are going to reduce y hat, right? So to increase this 1 minus y hat, you have to reduce y hat, right? Simple mathematics, right? So in this case, we are going to reduce y hat. So if y is 1, we are trying to increase y hat. When y is 0, we are trying to reduce y hat, right? So that is the loss function. In order to calculate the cost function, you have to take the sum of all the losses of each sample, right? So, if there are, generally we take m as the number of samples, right? In this case, so the cost is general, I think you can remember, cost is represented by J, right? So the parameters are given by W and B in that case. So the cost of W and B would be sum of I equals, so this would be I, right? Not 1. I equals 1 to M loss of yi hat yi. Right? So that means for each of the data point, we are calculating the losses and we add them for all the loss for all the data points in the sample, then divide by the number of data points. That is how you get the cost value. Right? So because we have already found this loss function is for the logistic regression is given by uh, binary cross entropy loss, right? So we uh, replace this loss value with the substitute this loss value with the real binary cross entropy loss. In this case, you can find all the other terms will be the same. In this case, you can have yi log y hat I plus 1 minus y hat log 1 minus yi hat. Right? So this is the uh, loss cost function for logistic regression. So when you are optimizing the values to get the optimum value for the logistic regression, okay, you have to uh, use gradient descent algorithm, which is an iterative algorithm, as you may remember. And so we are moving towards the path where the gradient is getting decreased, right? So you are taking the uh, cost value for each of the parameters. Here we only take, for simplicity, we uh, uh, take B bias can also be considered as weight, right? As W. So we just take W and with for each W values, we try to find for which W value you can get the least cost, right? For least JW. For that, you have to move. If you have started here, you should move here and here until you come to the lowest cost value, right? That is the uh, purpose of gradient descent algorithm, right? So you have to take several iterations until you come to the optimum point. In that case, you can use gradient descent algorithm like this, right? So this is the formula. This is the operation that you have to repeat until you come to the come very closer to the optimum point or the least cost point. In that case, we reduce the some value from the W, right? The reduced value is actually alpha. Alpha is the learning rate times differentiation of JW, which is the cost of the cost value, right? By differentiate the cost W by W, right? So JW by DW means you differentiate the JW by W, right? So you differentiate this function with respect to W. So this is full differentiation, right? Because we have only W variable. So in this case, because we have only considered W as the only parameter, but because there can be more than one variable, right? It can have, for example, W and B, right? So this JW by DW can become DABA because there are more than one parameter, right? So it would be J WB by DABA W or JWB by DABA B. So this is for the W and this is for the B, right? Uh, we have used DABA here instead of D because we have two more than one variables in J function, right? So this is the difference between a partial differentiation and full differentiation. If you don't have a sense, just forget it, right? So this is just the notation that we use it, right? So in that case, what we have to do is in each iteration, we have to change the W values like this as I have shown earlier, right? So like this one. So this is the simplest form that we have introduced, but in real, this is what really happens, right? So the W is reduced by minus alpha learning rate times DABA JWB by DABA W. So in the bias, sorry, in the bias is also reduced by learning rate times DABA JWB by DABA B, right? So there are two gradients in this case, right? So these are the gradient values. So this is the gradient for W and this is the gradient for bias, right? Okay, now let's see how uh, this kind of differentiation can be done in a bit different way. So not like not the way that we what we have already learned, right? But if you have a very complex set of learnings, right? So not just a single learning of a certain logistic regression, right? So you know how to do it, but when it comes to several such learning that are connected or concatenated with each other, you would need much complex graphs, right? So in neural networks, actually, you will find several logistic regression operate neurons are connected together. In that case, you would have to know how uh, several neurons or several logistic regressions are trained at the same time. That means how the uh, weights and biases are, or the parameters in simple, how the parameters in each of the logistic regression in each of the neuron is updated simultaneously uh, in a optimization function, right? So you know how to update, once you know how to update a, a simple or single logistic regression, then you can learn how to update the weights and the biases when there are more than one logistic regression learnings happening at the same time, right? So for the moment, let's learn how to do similar kind of thing using a concept known as computation graph, right? So you are not here. We are not going to talk anything about neural networks for the moment. For the moment, let's see how these computation graphs can be made as an inspiration for developing a training process for a neural network, right? So we haven't mentioned the neural network yet, but this is the way that we are going to learn about the learning process of a neural network. Right? For that, first say that you have a function j, which j is the cost function with a, b, c parameters. Right? So this function is to be approximated by a neural network. Right? So, so j is generally we take the j as the cost function, right? It can be cost function or not, right? So, however, we are going to this is going to be approximated by a neural network, right? So, in this case, we take the so suppose this the real function inside this j is 3 times a plus bc, right? Suppose this is the real, this is the actual function in between these variables, right? Between a, b, and c, this is the real function. Actually, you don't know this, right? So if you know this, you don't have to uh, train a neural network and find. You already know it, right? So suppose this is the one that is hidden in this neural network. So this is the real function that we are going to approximate with the neural network. Before we uh, draw the computation graph, first we have to drill down this function, right? So this j function into several steps, right? So because this function is bit complex, actually not complex, but we can simplify this into several steps, right? So for example, so in this case, what we are trying to do is we are trying to uh, construct this construct this function using primitive operations, right? So for example, b times c is a multiplication operation, times bc plus a is an additional operation, and a plus bc times 3 is another multiplication operation. So for each of the operations, we can have different steps so that we can uh, develop this function within several steps. So for the first step, we take bc and take the as u variable. Right? So we take u equals bc. Right? So now we want to calculate a plus bc. Right? So in order to do that, we take a plus bc as v. Right? V equals a plus bc. Right? Then we have already given name for BC, which is U, right? So we uh, substitute BC with U so that it would be V equals A plus U, right? V equals A plus U. By substituting U equals BC into this formula, you can get V equals A plus U, right? This is the second step. In order to get the J value, right? You have to multiply A plus BC by 3, right? So A plus BC is actually V, right? A plus BC is actually V, right? So we have to, so V times 3 times V is the J value, right? J is 3 times V, right? This is the V. So it would be J equals 3V, right? So now we have constructed several steps where we take BC as U and V equals A plus U, J equals 3V, right? Now with these three smaller functions, you can construct a computation graph. So by taking u equals b plus c, right? We take the initial variables from left side, right? A, B, C, and from we multiply b and c, and we get the u value, and we add the u to a plus u, we get the a variable and add with u variable, then we get the v variable, right? Then we multiply v variable by 3, and then you will get j variable, right? So that is what we want, right? So we wanted to explain j with a, b, and c, but because it is bit complex, we have used these computation graphs, and we have introduced some intermediate variables like v and u, so that we can simplify the computation process, right? So this is actually what we are going to solve with this computation graph, right? So these A, B, C are the inputs, right, to the graphs, and calculate the value as outputs in each of the node, right? So once you give some value for A, B, and C, like the x values, you can compute this u value, v value, and then finally j value using this computation graph, right? In this example, we take uh, a equals 5, b equals 3, and c equals 2, right? So for us example, we take these three values, right? And then we can calculate u, these intermediate values u and u value, u variable, v variable, and finally j variable using the computation graph. So this is the same computation graph. We have given a equals 5, b equals 3, and c equals 2. So from B and C, we can calculate the value for u. So u is BC. BC is 3 times 2, which is 6, right? So then we can calculate the value for V, right? So although we haven't mentioned, so when we have the blue color number nearby the variable, that means we are talking about this variable value, right? So B equals 3, A equals 5, C equals 2, right? So so when the number is nearby a box, that means it is about this variable, right? So U variable, it is 6, right? So because B is 3, C is 2, then U is 3 times 2, 6, right? Then this is the value for V, right? We says it's 11. So how the 11 comes? A plus U. A is 5, U is 6, right? 5 plus 6, it's 11, right? A plus U is 11. So then you want to calculate the J. J equals 3V. V is 11. 3V is 3 times 11, 33, right? So the value for J is 33. So by giving A, B, C as 5, 3, and 2 respectively, you can calculate the value for J is 33, right? So through the formula, right, uh, given in the diagram in neural networks, uh, you can find the values for each of the node and do the operations in each of the node, then come to the final value, right? So in order to find how the but the problem is that uh, when it comes to the a real neural network, we don't know what is the relationship in each of these steps, right? You don't know whether this v is equal to a plus u, or whether this u is equal to b times c, right? And this j is equal to 3v. We don't know, right? So if we know it, we can simply calculate it. But in neural network, what we are trying to do is we are trying to approximate these values, right? We are trying to find these relationships with the neural network, right? But we don't know it, right? So that is the problem, right? So that is the problem that we are going to solve with neural networks. So we are using the gradient descent algorithm to update the parameter weights in each step of the training process, right? So in each, so these are steps, right? So you can with gradient descent, you can change these values a little bit, and then you can find you can change this value a little bit and find how much this value will get changed. We can change this value a little bit and find how much this u value will get changed. We can change the u value a little bit and find how the v value will get changed, and so on, right? So that is how we, so by from one value to the other value, you can actually find how the other value will get affected when you change this value a little bit, right? When you change this value a little bit, what would happen to this value, right? So that means you can use apply the gradient descent in between these variables, right? So what we are trying to do with this gradient descent is that we are using this gradient descent algorithm to update the parameter weights in each step of the training process, right? So, so these are parameter weights, right? So, so there in each of the neuron, there would be things called weights, right? So as we discussed earlier, where there would be in the logistic regression neuron, there would be weight uh, matrix, and there would be X inputs and Y output, right? So and there would be a nonlinear logistic function, logistic function or any other function, right? In that case, we have a set of weights, so we have to find how to adjust these weights so that uh, the loss is minimized in each of the steps, right? But because this is not just a single process, right? So we are not using in here, we are not having a single logistic regression function, but there can be multiple steps, right? Involved. So in this case, we have to propagate the error, right? So when it comes to the gradient descent algorithm, we are using the error, right? Or the loss or the total cost to update the weights, right? But there are more than one logistic regression, so which are dependent, which have some dependencies from the earlier steps, right? So how to update the weights related to earlier steps? For that, you have to backpropagate the error or the difference from the real value to the earlier steps, and you update them accordingly so that you can apply the gradient descent in each of the step starting from the last step, right? So you can start from here, you can backpropagate the errors. Errors means the difference between the real value and the value we have predicted. So from that you can calculate the loss value or the cost value, and from the cost value you can update each of the weights in each of the parameters, right? So what are the parameters in this uh, computation graph? V, U, A, B, C, etc. Right? So you have to find how each of these parameters should be updated in each of the steps. So this is known as the backpropagation algorithm used in neural networks, right? So when it comes to uh, neurons, so although we haven't learned that much about neurons yet, you will learn them in upcoming lesson, right? So in order to learn that, before that, first we have to learn how this computation graph works, right? So in order to change the weights, you have to update these values, right? You have to update these parameters little by little, right? To ready to minimize the error, right? Minimize the total error. So for each of the parameter update, right? So what we do is the little amount of weight change has to be done on parameter compared to the little amount of change of loss, right? Has to be found, right? That is what we have to find. That means when there's a certain difference in J is the cost, right? When there's a certain little bit change in cost, how much this V variable should be changed, whether it is positive or negative, how much? And then how much the U variable should be changed, positive or negative, based on the this J change. Because due to this J change, how much this A variable change, positive or negative, to how much for this variable. For the B, how much? C, how much you should change. in which direction, right? So you have to update all these variables when there's a j change. That is what we have to do in this computation graph. So once you learn about this computation graph, you will understand how the backpropagation happens in a real neural network. Right? So suppose these parameters are given by W, right? So generally these weights are given by W, right? So when dabba j by dabba W means for how much uh, the weight should be changed uh, for uh, j cost, right? So this one is generally because this is bit large in size to write it. So this is generally represented by dabba W, right? So when you see dabba W somewhere, right? So that means so this is the j, which is the final parameter, right? Last parameter of this resultant parameter of this graph, right? So how much this parameter change should be happen with respect to each of the parameter, right? So in this computation graph, there's no W parameter, right? So but all the A, B, C, U, V, all of them can be considered as W parameters, right? So how much each of these parameters should be changed with respect to uh, how much this J should be changed uh, with respect to each of these parameters, right? And then you have to find how much each of these changes should be happened in each of the parameters. So you have to find dabba W for each of the parameter, like dabba A, dabba B, dabba U, dabba V, and so on, right? So in order to solve the computation graph, right? In order to find dabba J by dabba W, intermediate nodes related to partial derivatives also have to be found step by step. As I mentioned, you have to find go from start from the last and go from last to the beginning step by step, right? Starting from J at the final node, have to move back to the initial node. So you start from the J and you have to go to the V, U, A, B, C, and so on, right? You can remember, right? So this is known as the backpropagation algorithm. So in backpropagation, intermediate nodes related partial derivatives are found using the chain rule in calculus, right? So this is that something that you have to remember, right? So when you are calculating the changes that you have to happen, for example, if you want to find how much A should be changed with respect to uh, so, so for a somewhat change in J, right? So for in order to find that, actually you don't have this value, right? So what you can do is you can find instead of directly finding dabba j by dabba a, right? Because in this case, you can't find exactly how much j is changed with respect to a, right? But you can find how much uh, change uh, j has happened with respect to v, right? Because j is nearby adjacent to v, this node, right? And then you can find how much dabba v by dabba a, which is how much this node was changed with respect to this node, right? Similarly, you can use this as a chain and go to the last node, right? That is what this chain rule says. It says you can, instead of finding directly the dabba j by dabba a, you can use dabba j by dabba v times dabba v by dabba a, right? Dabba j by dabba v by dabba a. So with this node, you can find dabba j by dabba v. With this link, we can find dabba v by dabba a. So we will see how exactly we have to do it, right? So derivatives are calculated from the final node to the backwards, right? So in the next slide, you will see it, right? In red arrows, right? Uh, for example, let's increase the output j by 0.02 and see the changes. Actually, this is not what really happens. I will show exactly what really happens, right? So what you have to do is you have to, this is how in the green arrows, you can see how the computation happens in which direction, right? So you start from the ABC and you calculate U, then V, then J, and so on. But when it comes to updating the values from the for each of these parameters, you have to start from the last node, J node, and then you have to go in this red arrow direction. Then you have to go to this node, and from this node you have to go directly to A node. Then for this direction you have to go to the this U node, and from U node you can go to the B node and then C node. Right? So the computation happens uh, in this direction. This is not actually known as the forward propagation. What is given by this green arrow, right? And when you are updating the values in these parameters, you have to go to the back propagation. That means you have to start from the this last node, then go to the final to the initial nodes in this red arrow direction. So let's start with some values, right? So you can see I have used the same values that I have given earlier, like 5, 3, and 2, right? So you can calculate U as 6. That means BC is 3 times 2, 6. Uh, V is A plus U, which is 5 plus 6, 11. And J is 3 times 11, it is 33. Right? Right. So now what we are going to do is we have increased this variable, which is V variable, a delta amount or a very little uh, value, right? So what we can do is we can increase V by a very little amount, which is 0.01, right? We have increased V by 0.01, and then we have got V as 11.001, right? So then we have found what is the value happen that has happened to J, right? So in J, what is the value what is the value of J? J is 3V, right? So V is when the V becomes 11.001, J is 3 times 11.001, which is 33, 33.003. Right? So when you increase, listen carefully, when you increase V by 0.001, J has increased by 0.003. That means when V increased by a certain little bit, the J has increased 3 times. Right? So you can calculate, you can find dabba J by dabba V is 3. Right? Because when you increase a little bit of V, 0.001, then the J has increased by 0.003. Right? Because of that, we can say uh, the gradient or the ratio of J and V are 3, right? That, that is dabba J by dabba V is 3. So what happened is the partial derivative of J by V is 3. So I have used the small values in order for you to understand clear, right? So using these two nodes, by increasing a little by here and finding the effect in this node, you could find how much, uh, what is the uh, gradient between these two nodes. Right? So now here we can move to the other nodes, inside nodes as well in the back propagation. So let's move to the this node, right? So we have increased this 5 to by a little amount, which is 0.001. Right? So then it's already, so then the value of V would be A plus U, right? The U is 6, right? So 6 plus 5, A plus U is 5.001 plus 6 is 11.001. Right? So now what happens is when the A is increased by little amount, certain amount, the V has also increased by the same amount. Right? That means dabba V by dabba A should be 1, right? Dabba V by dabba A should be 1. Because when you increase a little bit in A variable, the V variable has increased in the into a into the same value, right? When 5 is increased by 0.001, the 11 is also increased by 0.001. Because of that, dabba v by dabba a is 1. Okay, now let's move to the other nodes as well. So we can increase 6 by little bit because 6 by 0.001. Then what happens is, uh, if this is 6 and u is 6, u is 6, u is actually now 6.001, a is, it is 5 already, right? So we don't use, so when it comes to partial derivatives, we are changing one variable at a time, right? So in this case, uh, because we are only changing u variable, we are keeping all the other variables unchanged, right? That is the idea of using partial derivative. That is why we are using dabba instead of d here, right? So you use 5 as a and 6.001 as u. That then the value of v would be 11.001. So then dabba v by dabba u is, because when you increase a little bit by 0.001 by u, then the v has also increased by 0.000. Sorry, v has also increased by 0.001. So because of that, dabba v by dabba u is 1, right? Just the same amount was increased in v. Then you can go to the b, and for that first we remove this value and then we add the value for, we increase the b value by 0.001, then to be 3.001, and then u would be, right? So the c is 2, right? So then u would be 3.001 times 2, which is 6.002, right? This is the value for u. Then what has happened when you increase b by 0.001, u has increased by 0.002. That means dabba u by dabba b is 2, right? So now we remove this value and we add the increment the c value by 0.001. Then what would happen? We use the original value for b, which is 3, and bc is 3 times 2.001, which is 6.003. So when you increase c by 1, c by 0.001, u has increased by 0.003. Then dabba u by dabba c is 3. Right? Similarly, you can now you can see how we have calculated the partial derivatives with respect uh, uh, to the right hand side variable, right? So right hand side variable is partial derived by the left hand side variable, and we can find the partial derivatives, right? So if you can remember all these partial derivative variables, you can use the chain rule, right? Like this, and you can calculate all the partial derivatives with respect to uh, that means all these partial derivatives like dabba j by dabba a, dabba j by dabba b, dabba j by dabba c, right? So in the earlier case, you can't directly find the dabba j by dabba a, right? So but here, because now we have dabba j by dabba v and dabba j by dabba v and dabba v by dabba a, you can calculate dabba j by dabba v directly, right? Sorry, dabba j by dabba a directly, right? Which is this times this one, which is 3, right? 3 times 1, 3. Dabba j by dabba v times dabba v by dabba a, which is 3 times a, 3 times 1, 3. Dabba j by dabba b is dabba j by dabba b is dabba u by dabba b, dabba b by sorry, mm, yeah, dabba v by dabba u, right? Times dabba u by dabba j by dabba b, right? So once you multiply this term, and this term, you can get the value for dabba j by dabba b. Right? Here you can see 3 times 1 times 2 is 6. 3 times 1 times 2 times 1 times 3 is 6. Right? Similarly, you can calculate the values for uh, dabba j by dabba c, which is uh, dabba u by dabba c, this value times uh, dabba v by dabba u, this value, and dabba j by dabba v, this value, right? So by multiplying these three terms, you can get 3 times 1 times 3 is 9 for dabba j by dabba c, right? Dabba j by dabba 3 is 3 times 1 times 3, which is 9, right? So if you are not that much familiar with this chain rule or calculus at all, just uh, take some time and carefully go through this calculation so that you will understand these calculations clearly, right? Okay, so this is very simple uh, calculation. It is very easy to understand, right? So in this case, so how you, if you want to see how the chain rule was applied, you can see like because when you can't really find this value, what you have done is you have added dabba v from bottom and up, right? So mathematically, if you try to cancel out this dabba v and dabba v, so this dabba j and dabba a are there, right? So this dabba j is there, dabba a is here, right? So you have added dabba v here, right? So you can find this one and this one. Because of that, you can multiply these two terms and find this value. You can't directly find this term. What you can do is you have dabba j here, dabba b here, right? So instead of finding this one directly, you have added dabba v here and here, which will be getting cancelled out. Dabba u here and dabba u here, which will also get cancelled out, and you will get dabba j by dabba b, this part. So, right? So you can find these three terms individually, and then you can find the final value by multiplying all of them in the chain rule. Similarly, you can find the value for dabba j by dabba c by dabba j here, dabba c here, and you have added dabba v here, here, and here. So they will get cancelled out. Dabba u here and dabba u here, which will get cancelled out. And you can find these three terms individually, 3, 1, and 3. Then you can multiply these three and get the final value for dabba j by dabba c, right? So that is how you find how each of uh, these uh, these gradients should happen. That means how each of these gradient values should be changed with respect to uh, how each of these values should be upgraded when the j happens, right? So use so this is actually about backpropagation in logistic regression, right? So we use the this computation graph technique for calculating output values using the forward propagation, right? So like we have the values for a, b, and c, and we calculate in the green arrow direction, and we calculate the values. So that is when you are making predictions, right? You can use the forward propagation to make predictions, and in order to, when you are learning, you have to use the calculate weights and bias changes with respect to output rate of change, right? Using the backpropagation, right? So output rate means cost change, right? With respect to the cost change, how much each of these weights, weight parameters, where A, B, C, V, U should be updated, right? So those things should be calculated using the backpropagation algorithm in the backward direction, right? This approach can be used to calculate the updates to be done on weights and biases of a unit of logistic regression, right? So, so we have just we are we can simply show how this can be applied to a logistic regression node, right? So we are not going too deeper into neural networks how we do it, but for a logistic regression unit how it can be done, right? So these are the formulas. If you have forgotten, so these are the formulas for logistic regression. Z equals WTX plus B, right? So this is the linear combination, right? So this Z would be a linear value. So then you apply the logistic function sigma to Z, and then you get the, so this is the activation value, right? This is the, this activation value is the, actually the output value or the Y value, right? So this is the loss function of logistic regression, where this is the output or the prediction value. This is the ground truth value or the real value, and this is the binary cross entropy loss, right? I think you remember these three terms, right? Now let's draw the computation graph of logistic regression using the above computation phases, right? So this is something that I have taken from uh, the online course from Andrew Ng. So you can find how uh, this loss value is back propagated in each of the direction to the backward direction, where you take this output value or the predicted value and the real value, and in red arrow direction you take the activation function, sorry, activation value, which is the uh, value that you get after the uh, logistic function, right? And then you can move into the linear functions, where w1 x1 plus w2 x2 plus b, the, and we can come to the z value. From the z parameter you can calculate the x1 w1 x2 w2 b, those parameters, how each of these parameters are calculated. So this is we are not going too deep into how the calculation mechanism, because we have already found some intuitive way to calculate these values. But you can understand this, in this way you can actually calculate how each of the W1, W2, and B values should be updated with respect to the gradients that we come up with using this backpropagation algorithm, right? So we are not going deeper into in detail how these calculations are done, and we are going to finish this lesson for today. If you have any questions, you can ask.